Today is really exciting. So up until now, we reviewed a bunch of pre-calculus stuff. We went over limits. The limits are going to help us to find a derivative, and that's what we're doing today. That's why it's exciting. Derivative calculus is made up of two parts. You have derivatives and integrals, and so now we're going to actually take our first derivative today. To kind of understand what's going on with derivatives, we talked about how with calculus you could find instantaneous rate of change. In the last chapter, we found average rate of change. So for example, if I wanted to find out what's the instantaneous rate of change at that point, I could approximate it by finding the slope of this line. And this line is called a secant line. A secant line is a line that crosses a curve twice. So you can see it crosses there and it crosses there. So if I want to find the average rate of change, I could find the graph of that secant line, and I could approximate the instantaneous rate of change there. That's not going to be very accurate, though. What I could do to make it more accurate is I could start moving back. Like I could do that secant line there, be even more accurate. And you can look at the average rate of change. Right now it's at 0.47. But as I go back, and that secant line, as the points get closer together, it's going to be closer and closer to the slope of the tangent line. The tangent line is a line that touches the graph in one location. It turns out that if we can find the graph of the tangent line, then we could find the graph of the function itself. They have the same, the graph at that point on the curve. They have the same slope. So what we're trying to do, and what calculus does, is we want to take that distance from here to here, that x distance, we want to make it as small as possible. The problem is once I get back so they're both the same point, it won't work anymore because I go y minus y over x minus x, I'll end up with 0 over 0. So what we're going to do is take the limit as that distance approaches 0. So as that distance gets closer and closer to 0, it'll get closer and closer to that instantaneous rate of change. If I take the limit as, and we call that the change in x, remember that triangle x, I go the limit as that change of x approaches 0 and it's just the slope formula. So the way the slope formula works is I take the upper y coordinate, we call that f of x plus delta x. That's just this y coordinate right there, minus the y coordinate at the point, that's f of x, all over the change in x. And the change in x is just this distance right there. Well, that distance, we call it, that is a change in x, right? Delta x. So this is our formula. And if you open up your books to 1.2, this is a formula that they give you right there. But the idea is this. This part is really just the slope of the secant line. And what we're doing is we're finding what happens as that distance between those 2 points. I'll slide it back a little bit. The distance between those 2 points, as it approaches 0, it gets closer to 0. What's going to happen is we're going to get closer and closer to the actual tangent line. And if we can find the slope of the tangent line right there, that gives us the instantaneous rate of change. You can see how they just outlined it in other colors. So let's go to the actual formula. This is in your book. And this first part is really just covering what we just talked about. But what it's saying is if you have the secant line, I'll outline it in a different color. If you have the secant line, right, there's my one y coordinate, f of x plus delta x. There's my other one. That's what goes up here, right? Y minus y, divided by the change in the x. So if I take x delta x minus x, and you find that change, it comes out to be delta x down here. So that gives you the slope of the tangent line. The secant line. To find the slope of the tangent line, then, we just take the limit as delta x approaches 0. So as this point gets closer and closer to x, we just look and see what's happening to the slope of the secant line. A couple of things. Just to review, this is important. You can underline this in your book here. It says the slope of a curve is defined by the same as the slope of the curve's tangent line at a given point. So if you're asked to find the slope of a curve, it's exactly the same as the slope of the tangent line. So that's really what we're looking for, is the slope of the tangent line. The slope of a tangent line is called the derivative, right? So that's what we just talked about. We're going to find our first derivative today. The most common used symbol is this f prime of x. If you guys remember that little tick mark from geometry, it's f prime of x. Some other notations are, instead of f primed, you can do y primed. dy dx, that's the way you say that, dy dx, that means the same thing. It means find the derivative of y. Sometimes they say that find the derivative of y with respect to x. And we'll talk about more about that in just a second. This is the same thing, d dx of f of x. Again, that just means find the derivative of f of x. So all of those mean the same thing. And what we're really doing is we're finding the slope of the tangent line. Okay, this is our formula. We're going to find the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. This one, I use this a lot more. Instead of delta x, I just have an h. That's all that's happened. I just like it because it's easier to write than delta x. So it doesn't matter whether you put a delta x in there or you put an h in there. I've seen it done both ways in books. Vertical tangent line has no slope, right? If you have a vertical line, it has no slope. So if you have a derivative that has a vertical tangent line, that means at that point it has no slope. That means it does not have a derivative. Differentiation is a process of finding derivatives. If a derivative exists at a point on a curve, the function is said to be differentiable at that point. So again, that's just some vocabulary right there. Okay, let's find our first derivative. So it says if f of x equals x squared plus 2, find f prime of x, which again means to find the derivative. Okay, so we'll set up our formula. The formula is the limit as delta x approaches 0 of, and I do f of, whoops, sorry about that. I do f of x plus delta x minus f of x all over delta x. So let's start first with this point right here, f of x plus delta x. That means, this function right here. We're going to take x plus delta x and plug it in for x right there. So that would give me x plus delta x squared plus 2. So that part right there is simply that part right there. Minus, the next part is f of x. So let's take what f of x is. Well, f of x is just x squared plus 2. Make sure you put that in parentheses. So there is f of x plus delta x minus f of x all over, and then we just have a delta x down here. Okay, now it's just a matter of working this out. So this requires just a bunch of algebra. I'm going to take x squared plus, I times the 2 together and times it by 2. That'd be 2x delta x plus delta x squared. That's just multiplying that part out. I still have the plus 2, carry the minus through, so it'd be minus x squared minus 2. And that whole thing is above delta x. Okay, we can combine some like terms. I've got x squared minus x squared. I've got 2 minus 2. So when I get done with that, that leaves me with 2x delta x plus delta x squared all over delta x. I should be doing this the whole time too. I apologize. This is the limit as delta x approaches 0. The limit as delta x approaches 0. The limit. And the reason why I'm having to do all the simplifying, right? I kind of got ahead of myself, but if I come back up here to find the limit as delta x approaches 0, if I plug 0 in, I get 0 on the bottom of the fraction, which we can't have. So I'm trying to simplify this using these algebraic methods to make it so I can plug 0 in. So now if I look at the top, I can factor out the delta x. That would leave me a 2x plus delta x all over delta x. And the reason why I did that is because now those reduce. So now I'm going to find the limit. That's really what I was looking for, because now I can plug 0 in because there's not a delta x left on the bottom. So if I plug 0 in for delta x right there, I get 2x plus, and I'm plugging 0 in for delta x. So it really just comes out to be 2x. So after all that, my derivative, f prime of x, is equal to 2x. So what that means is I now have a formula that no matter where I go on that graph, my graph is f of x squared plus 2, I can plug in the x value into my derivative and I know the slope at that point. So here's an example where I've got this function right here. If I want to find the slope when x is 1, all I do is plug 1 in there. So f prime of 1 2 times 1 is 2. So the slope of that line is 2. Or if I do it 0, f prime of 0 is equal to, and the slope, think of the tangent line would be like that. So the slope is 0. If I plug 0 in there, I get 0. Now up here it says find f prime of 3, negative 3, excuse me. All I do is plug negative 3 in there. 2 times negative 3 is negative 6. So that means at this point, at negative 3, somewhere, this graph keeps going up, somewhere right up there at that point, the slope's going to be negative 6. So that's what the derivative does. It allows us to find the slope at any given point. Let's try another one. So this one is f prime of t is equal to 2 over t, and we want to find the derivative. So number 2 here, you have y equals f of t equals 2 over t. It says find the derivative of y with respect to x. This respect to x tells you basically what the variable is that you're using. In this case, instead of x's in our equation or in our function, we have t's in our equation or in our function. Okay, so we're going to start out, use our formula. So f prime of t is equal to the limit as, I'm going to use h this time instead of delta x, but it doesn't matter. You can use either one. So the limit as h approaches 0 of f of h plus t. So that would be 2 over, and in place of that t, I'm putting h plus t. I'm going to switch those around, actually go t plus h. We'll do it the same way the formula has it. So t plus h minus f of t, that'd be 2 over t, all over h. So that's just using our formula. This is the f of t plus h, this is f of t all over h. So if I plug 0 in right now, right, I get 0 on the bottom of the fraction. So I've got to do some algebra to simplify this. So the way we did this, we did a couple problems with complex fractions before, but not a lot. What we want to do is get rid of those fractions within the fraction. So what I can do is take that top part, and I can times by the least common denominator. Well, this one has a denominator of t plus h. This one has a t. So they both have to be part of that LCD, the least common denominator. So I'm going to times by t times t plus h on the top and the bottom. And this is what happens. When I multiply through there, the t plus h and the t plus h cancels out. That just leaves me with a 2t. When I multiply it through here, the t and the t cancels out. That leaves me with a 2, and I still have a t plus h. So that's a reason why we multiply by that LCD, is we get rid of all those smaller fractions within the bigger fraction. On the bottom, I still have h times t plus h. What I'm hoping will happen is that I can get an h on the top that will cancel out with this h down here on the bottom. Okay, let's simplify the top. Distribute that minus 2 through. I get 2t minus 2t minus 2h. The 2t minus 2t cancels out. I get negative 2h over h times t plus h. And that's a good thing because now I can take the h's and just reduce them down. So now I can come back over here. I haven't been writing my limit, but I need to. I have the limit as h approaches 0 of, that h canceled out and that h canceled out. So I have negative 2 over t times t plus h. And now I'm going to plug 0 in. So if I plug 0 in, I get negative 2 over t times, and this t plus h, if I plug 0 in for h, there's no h left. So there's t plus 0 is just t. So I'm going to put t times t. So my derivative, f prime of t, is equal to negative 2 over t squared. So you'll see the hardest part, the trickiest part in these problems is the algebra. It's not the calculus itself, but there's a lot of algebra involved in order to find that. All right, let's try this next example. So I kind of got out of order here. I don't know how it got mixed up. Let's go to this example number 2 right here. It says y equals the square root of x. We want to find y primed. So good, we're just using our formula. We're going to find the limit as h approaches 0 of f of x plus h. I plug x plus h in for x, minus f of x, that's just the square root of x, all over h. Okay, if I try plugging 0 in, I get 0 on the bottom. That doesn't work. So one of our tricks with algebra, if you remember, is if you have square roots, we can get rid of them by timesing by its conjugate. So if I have the square root of x plus h minus the square root of x, I can times it by the square root of x plus h plus the square root of x. Those two are conjugates, but if I do it to the top, I have to do it to the bottom. Well, what happens up on top, right? When I times those together, that gives me x plus h. This is the limit as h approaches 0. So I have x plus h. That's going to be a plus square root of x plus h times the square root of x. This is going to be a minus square root of x plus h times x. They're going to cancel each other out. But I do have a minus square root of x times the square root of x would be the minus x. On the bottom, I still have h times square root of x plus h plus the square root of x. Well, what happens up on top is those cancel out. Well, that leaves me with a factor of h. So now I have h over h times the square root of x plus h plus the square root of x. And now I can cancel out those h's. So I'd have a 1 up there on top. So now I have the limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. Okay, now I'm going to plug 0 in for h. That h right there is going to go away right there, right? It becomes 0. So I have this equals 1 over, I'm going to come up here, hit another dead spot there. So it's 1 over, I'd have square root of x plus the square root of x. So my final answer, see if I can get around that dead spot right there, is going to be, we started out with y. So I'm going to say y primed, the derivative of y, is 1 over, and if I add the square root of x plus the square root of x, it just comes out to be 2 square root of x. And there's my derivative right there. All right, so that was 2, we did 3. There's one other little problem here, and that a different type of problem. We've just been doing the limit definition of the derivative. We're going to now look at what's called the alternate form of the limit definition. And what it does is instead of finding the derivative, an equation that gives you the derivative for any point, what it does is it gives you the derivative at a single given point. So notice before we had an x down here, now we're saying it's a c, it's a constant. So what this is going to do is it's not going to give us a formula. Instead, it's going to allow us to find the derivative just at a single point. Well, that's not as helpful to us. So if I have an equation for the derivative, then I can find it at any point. That's a lot more helpful. But this is a little easier to do usually. And so that's the advantage as well. It doesn't give me an equation where I can find it at any point. If I only need a one given point anyway, I can use this alternate form of the limit definition to find it at a single point. So that's the important thing, is this only gives you a single point right there. So the formula is this. I find the limit as x approaches c of, I just go f of x minus f of c all over x minus c. So the formula is a lot simpler to find. All right, so we got this problem. It says f of x equals x cubed. It says use the alternate form of the derivative to find f prime of 3. So the reason why I would use that here, again, is because I'm finding it at a specific point when x is equal to 3. Here's our formula right here, if you want to have that in front of you. So if I'm finding f prime of 3, I take the limit. Now, instead of being as h approaches 0, it's as x approaches whatever c is. C is the point where you're trying to find the derivative. That's when x is 3. So I'm going to say the limit as x approaches 3 of, and on top I go f of x minus f of c. F of x is x cubed minus f of c. That means I plug 3, that's f of 3. So if I plug 3 in there, 3 cubed is 27. All over x minus c, that'd be x minus 3. Okay, I just need to work this out. If I plug 3 in right now, I get 0 over 0, right? So that means that I got to do some algebra to try to simplify this. It's probably a hole in the graph. So I'm going to take this x cubed minus 27 and try factoring it so I can reduce it. So that's a difference of cubes. So the way it factors is x minus 3. Then I take the first term x and square it. I times the two together, which is 3x and then take the 3 and square it. So that's just the difference of cubes formula we've used before. All over x minus 3. And that works out nice because the x minus 3's just cancel out. Now I can have the limit as x approaches 3 of x squared plus 3x plus 9. Okay, now I can plug 3 in. So if I plug 3 in, I get 9 plus 9 plus 9. So the answer comes out to be 27. So f prime of 3, or the derivative at 3, comes out to be 27. So you can see how there's less algebra involved. It makes it a little bit simpler. The drawback is this, is it only tells me the derivative when x equals 3, right? When we did the limit definition of the derivative, we got an equation where I could plug anything in for x I wanted, and I could find the derivative at that point. So this one only gives you the derivative of a single point. If that's all you're looking for, this is quicker and easier. But again, it's not quite as helpful because we're not given the formula where we can find it at any point. So those are the two things you're practicing. You'll see 1 through 5 on your assignment. You're finding the limit definition. On 6 through 9 on the assignment, you're finding using the alternate form. The rest of it, so you're going to be doing some reviewing, including the last section. Actually, it's some really simple stuff. It's like adding, subtracting fractions and some exponent rules. But that'll be really helpful to us as we go into 2.2, into the next section there. All right, that's all I got for you. Thanks, guys.